So the final talk of the workshop, this is the best for the last. So quantum entanglement, sum of squares, and log-rank conjecture. Pravesh will be.
Hi, thanks Prasad for inviting me, and thank you all for staying for the absolutely last talk, the grand finale of this awesome workshop. So so I'm going to tell you about quantum entanglement, sum of squares, and the log-rank conjecture, joint work with Bose Barak and David Stoider. I guess a couple days ago you saw like some technique to prove lower bounds for sum of squares, the pseudo calibration. Then this morning, Slil and David told you how to design average case algorithms for average case problems using sum of squares, and this talk is going to be about worst case algorithm design using the same technique. So in particular, this is going to be about a problem that for now I'm going to call the find a rank 1 matrix in a subspace problem. And that's going to be a mouthful, but I'm going to stick to it because this problem comes from some quantum information motivation. I'm going to tell you that motivation in a bit, but I won't carry around that name for the purpose of the talk. So the talk is going to be completely classical. Great. So in this problem, you're given a basis that spans a linear subspace of n by n matrices. Okay? And you're promised that there is a rank 1 matrix which is completely contained inside the subspace. So this rank 1 matrix is described by two unit vectors u and v, and uv transpose, there is some uv transpose that you're promised lives in this subspace w, which is given as input to you. Your goal is to find some rank 1 matrix described by some unit vectors x and y, so that xy transposed is in this subspace w. Okay? So here is my lame attempt to make a drawing for this problem. So in some sense, this is a question of finding a point in the intersection of two sets. Both the sets are actually extremely nice and well studied. One of the sets is just the linear subspace, which is actually input to the problem. The other set is this manifold of rank 1 matrices. It's an algebraic variety in the sense it's basically a solution to a system of quadratic equations. The issue, of course, is that we know how to find points in the intersection of two convex sets by standard convex optimization machinery. But one of these sets here is, while it's nice, it's not really convex. So, we, for example, cannot apply standard convex optimization machinery to find a point in the intersection here. Okay? Great. So, just to tell you why it's a problem of this problem itself can be thought of as just a problem of finding a solution to a system of quadratic equations. Here is sort of a simple formulation to convince you of that. If B1, B2, BR is a given basis to me, for that spans the subspace W, then I'm looking for some linear combination which is described by coefficients C1, C2 up to C small r, so that some Ci Bi equals xy transposed. Xy are also my variables here. So in particular, this is a quadratic equation in x, y, and c's. And to force non-zero solutions, I can add some constraint that says that the L2 square norm of x and y has to be, let's say, 1. Okay, so you all agree that this is a problem of finding solution to a system of quadratic equations, and this is going to be what bothers us for the last 20 minutes or so. So just to tell you that I'm not super concerned about finding a point in the exact intersection. I would be happy if you give me some rank 1 matrix which is close to the subspace, but that leads me to the question of what is the right notion of distance in this context. So really, in some sense, I could have thought of this question as finding some vector in an n² dimensional Euclidean space. I'm just thinking of them as n by n matrices because the structure on the vector that I'm looking at is the rank 1ness, and it is sort of easily understood in terms of matrices. Okay? But that also suggests the right notion of distance. The distance notion would be the Euclidean distance of a vector from a subspace. In the space of matrices, it goes by the name of Frobenius norm. So what you want is that xy transpose, when projected to this subspace W, linearly projected, should basically be I should get almost all of the Frobenius norm back. So up to, let's say, some 1% error. Okay, so in fact, so that's the notion of distance. And moving forward, I'm going to basically fix this epsilon to be 0.01, just 1%, so that I don't have to carry around extra parameter. One other simplification I'm going to do moving forward is that instead of looking for rank 1 matrices with like two vectors, so like asymmetric rank 1 matrices, I'm going to look at symmetric rank 1 matrices. This makes no difference to the algorithm analysis or the result, but just like one less vector for me to worry about. So are there any questions about the problem? The problem definition is clear? Okay, great. So so now I want to tell you about a little bit about where this problem comes from. There's obviously a direct motivation from quantum information, but I also want to remind you that if you don't care about the quantum information part that much, this is an example of what I like to call a structured eigenvalue problem, and you've seen several examples of this, hopefully, in other forms. Basically, this is a question of so you're given some subspace, and you're interested in finding, vectors in a subspace that satisfies some additional structural property. So for example, this structure could be Booleanity, and this corresponds to max cut, or this structure could be like sparsity, and it corresponds to small set expansion. If you care about machine learning, then there is some other like sparse PCA-like problems that fall into this regime. So the problem that we are interested in today is sort of where the structure itself is this rank oneness when the vector is looked at as a n by n matrix, and you're interested in finding such a vector in the subspace. So it's an example of a structured eigenvalue problem. This particular problem goes by the name of best separable state. This is the name I was avoiding in quantum information. And the subspace actually comes from top eigenspace of a certain matrix called as the measurement matrix. Again, not important for this talk. But the reason we care about this algorithmic problem is that, this algorithmic problem stands at sort of this position where we want to understand this difference between entangled quantum states and separable quantum states. So in some sense, this problem is sort of like one angle to studying separability versus entanglement. And again, not important if you don't know what that is. Very concretely, there is a quantum complexity conjecture which relates to characterizing the power of two-prover quantum proofs. And if this problem has a fast enough algorithm, like a quasi-polynomial time algorithm, then it turns out that somewhat surprising complexity class collapse happens. And that's one reason to sort of care about this problem. If you design a fast enough algorithm, something nice, or depending on where you are, something bad happens. But again, not super important for us. Hopefully you like the problem by itself, and you are interested in designing a fast algorithm for it regardless.
So in the quantum application, does W have any structure here for getting in this abstraction?
Perhaps, but I don't know if it's a usable structure. So the W comes from top eigenspace of measurement operators on bipartite quantum systems. Perhaps that's not the most general subspace. I have to think about it, but I'm not sure there is. Yeah, I can't think of any usable structural information that I'm losing in this formulation.
So usually in the separable thing, you have like a biquadratic structure.
Right. So that sort of yeah. So this is the view. Okay. So you can think of states. Okay. If there are pure states, you can think of them as density matrices or vectors. And in this world, I'm adopting the vector view in some sense. Really, what you're supposed to think of these as, like this corresponds to the density matrix, which is like, so if it was UV transpose, it corresponds to the density matrix UU transpose tensor product VV transposed.
I'm trying to understand this. Otherwise, you lose a separability, right, between the U and.
Right. So all I'm saying is that in this form. So
U itself will be a tensor product.
Right. So U basically stands for the pure state with the density matrix UU transposed. Does that make sense?
Should it be UV transpose here?
Yeah. So I'm sticking to the symmetric version now. Yes. In general, it would be an asymmetric version. For the algorithmic purpose, I'm going to stick to the symmetric version now. Okay. You can forget about the quantum application for now, and we can take it offline. Okay. Good. So what do we know about this problem? So quantum folks have figured out lots of cool stuff about this question. In particular, we know that if you make this epsilon thingy here very, very tiny, like something that goes to 0 with a dimension, then it's going to be NP-hard. In fact, even if I make this like a fixed constant like 0.01 that we care about today, it turns out that there is a quasi-polynomial lower bound if you assume that 3-sat cannot be solved in 2 to the little of n time. Okay, and in some special cases, so when the subspaces W are somewhat special subspaces that arise from top eigenspaces of some special measurement matrices, then there is in fact a quasi-polynomial upper bound for this problem. But the bottom line is that there is no non-trivial algorithm. By non-trivial, I mean something that does not do brute force search over all possible vectors over the unit sphere, which runs in like 2 to the O of n time. There is no non-trivial algorithm for this problem for general subspaces. Okay, that brings me to the main result. The main result is like a slightly non-trivial algorithm for this problem. This is going to be a 2 to the root n time algorithm up to polylog factors for this find a rank 1 matrix in a subspace problem. And this is going to be based on rounding, some sum of squares relaxation for this problem. Okay, and there are some quantum corollaries that we can safely ignore. Great. Are there any questions? Okay. So now I'm going to tell you about the algorithm. And before telling you about the algorithm, I'm going to pontificate about the general approach of algorithm design using convex relaxations. So bear with me. So here is how we are taught how to design algorithms. We say, well, we start with some intractable formulation, I don't know, quadratic equations or integer programs or whatever. And then you choose a convex relaxation for this problem. So if these red points sort of denote, let's say, the set of all x's that satisfy the system of quadratic equations that we care about in the present context, then in some sense, the tightest possible convex relaxation you would want to choose is the convex hull of these points. But usually you don't know about these points. In some sense, that's the whole problem, that you don't know this convex set. So you choose some relaxation that would definitely include this convex hull. Okay? Then you use some generic technology to find a point inside this convex set, let's say using ellipsoid. And then you have to do this task of rounding, which is take a point inside this larger extended convex set, the relaxation, and map it to something that is close to a real solution, right? And I want to remind you that the set of rank 1 matrices is not convex, which means that it's not enough to project this point over this polytope. You really want to get close to one of the vertices. Okay? So that's the rounding problem. But of course, there was a twist. Even though this is, so the point I want to make is that even though the algorithms papers are written in this linear way in which the relaxation happens and then the rounding happens, I want to say that actually in many cases the rounding informs the relaxation and the relaxation sort of drives the rounding, and it's not really a one-sided affair here. And the point being that you have some basic relaxation, you start rounding it, and in the analysis you discover that, wow, it would have been nice if I had this inequality that my solution satisfied. So you go and satisfy, add that inequality like hyperplane to your convex relaxation, make it like stronger, and you continue your analysis. Maybe you do this back and forth a couple of times, and eventually you end up with a relaxation that is sort of tied down to your rounding, that helps your rounding, right? So in other words, I want to say that it's not strictly speaking correct that the relaxation happens before the rounding. In many cases, the rounding sort of informs the relaxation we actually choose. Okay, and to correct years of injustice in presenting algorithms papers, what I'm going to do is present the rounding first and give you the relaxation later, or perhaps never. So okay, so that was our quadratic equation system that we were interested in solving. So in this approach, we don't care about choosing the right convex relaxation. We just choose the tightest possible convex relaxation ever, which is the convex hull of the actual solutions. And of course, I don't know this set. That's the whole problem. But I'm going to ignore that issue for now. Okay? I'm going to imagine that there is an oracle that finds a point inside this set. Okay? So somebody gives me this point inside, and I worry about the problem of rounding, which is given a point inside this convex hull, how do I map it something close to a vertex of this polytope? Okay, I'm going to call this a rounding problem. Okay, and now what you do is you come up with some rounding procedure. Hopefully it's nice, simple. You go and dive in to find what do you require in the analysis of this rounding procedure. This is similar to what Still was saying in the context of tensor decomposition. You want to find out the constraints that were really important, the hyperplanes that were sort of satisfied by the actual solutions. You want to find out which one of them were really important in your analysis, and then hopefully there are not too many of them. Hopefully not all of them are really required. So you go and add only those hyperplanes or only those constraints that were useful in your analysis. Hopefully this will be a small set, and you will end up with like a small convex relaxation. And in some sense, since your rounding only used the fact that the rounding sort of used only this subset of the hyperplanes that were satisfied by the actual set, in some sense you actually managed to show that even if you find a point inside here, the transformation that you do in the rounding would end up mapping it close to a vertex of this polytope. So in some sense, you didn't really use that you were inside this convex hull. That's what your argument already showed. Okay? So this is all vague, and I'm going to make it concrete in a second. But hopefully this abstract, mumbo jumbo makes some sense. Great. So now we're going to try to implement this approach for our problem. So we first want to start with the tightest possible convex relaxation. So that I said is the convex hull of the actual solutions. I'm going to think of them as distributions over x's that satisfy the system of quadratic equations here. Okay, so that's great. So now I have a distribution, over x's that satisfies the system of quadratic equations. Later on, I do want to make an algorithm out of this. So looking ahead, I realize that if I come up with a rounding algorithm whose input itself takes like a huge space to represent, then I'm in sort of deep trouble in trying to make that whole step algorithmic later on. Okay, and here I face that issue because this mu could take exponentially many parameters to describe. It's a distribution over the unit sphere. So for all I know, it could be supported on exponentially many vectors. So what I want to do is somehow like reduce the number of parameters in order to sort of have some chance of making this whole thing algorithmic later on. So here I'm going to do the first lossy step. I'm going to make an ansatz that I'm going to look at only degree up to d moments of this distribution mu. Okay? This is an artificial tactic I'm going to play just so that the number of parameters of the distribution requires to be specified are n to the O of d now. So if d is like non-trivially smaller than n, then at least I have a small object that I'm thinking about. Okay? So my problem now becomes, given degree d moments of a distribution mu supported over x's that satisfy the system of quadratic equations, how do I map it to a point close to one of the actual solutions? Okay? Great. So that brings me to the main step of the proof, the rounding algorithm. And this, in some sense, is sort of the conceptual heart of the proof. In some sense, the next steps, it's not like they need to be done, etc. But they are basically the technical things that you need to do at the end to have an algorithm. But in some sense, all the conceptual ideas happen in this step 2, where you want to somehow round just an actual distribution from low degree moments. Okay? Great. So just to remind you, here is our problem. I have a distribution, in fact, low degree moments of a distribution, which is supported on actual x's that satisfy the system of quadratic equations. I thought I was not saying anything controversial, but okay, so our rounding problem is that I have degree up to d moments of this distribution, supported over x's that satisfy the quadratic equations, and I want to get to like some single x star, a unit vector, such that the rank 1 matrix defined by it, is close to being in the subspace W. Great. So here I'm going to do. Let's see how it goes. So let's try to do this proof. Say mu is uniform over some set of vectors u1, u2 up to u capital N. Okay. Now, without loss of generality, I'm always going to think of distributions as uniform over some set. And this sort of is sort of without loss of generality. But even if you don't see it, just imagine that these are all the distributions I care about for some reason right now. Okay. Now this n, by the way, could be really huge. As we talked, the distributions could be supported over some like a full epsilon net of the unit sphere, and then it could be like exponentially large. Okay. But all we know is that for every ui in this list, ui transpose lives in the subspace W. Okay. So and since I'm only going to think of this uniform distribution, I'm going to think of distributions and sets interchangeably from what happens in what happens further now. Okay. Great. So now if I had one wish to ask the genie, I would ask like for the set of rank 1 matrices to be convex. Okay. And I want to convince you that if the genie granted this wish to me, then I'm really done. Okay. So here is the simple argument. Say the set of rank 1 matrices was convex. It's not. Okay. But so say for the purpose of this argument, it happened to be convex, in some parallel universe. Then if I take the expectation of ui transpose with respect to the distribution mu, which is basically uniform, so it's just 1 over n times sum of ui transpose, then this is a linear combination of this rank 1 matrices ui transpose. So in particular, it lives in the subspace W, linearity, right? And this is also a convex combination. If the set of rank 1 matrices were convex, then this would be itself a rank 1 matrix. So that's awesome. I have a rank 1 matrix in the subspace W, so I round and be done. Okay. One thing to notice also is that this expectation has entries which are just degree 2 moments of the distribution mu. So I don't even need the whole distribution mu for this algorithm to work. I just need the first 2 moments, right? Okay, so we are in a great, awesome world if rank 1 matrices were convex, but even the genie tells you that you should not ask for something stupid. So this obviously is not the greatest idea in the world. So, but we're going good. So we want to somehow relax this notion of convexity that was useful to us, and still make this, get some non-stupid version of this idea to work. Okay. So this may offend some of the people, and if this notion of approximate convexity bothers you, this never appears in the paper. So feel free to read the paper, ignore the talk. Okay. This notion exists only in the talk. But hopefully it will make sense to you. So this approximation of convexity is designed just so that my rounding argument that I was telling you in the previous slide can work in some sense. Okay. So I would say that the set of rank 1 matrices is delta convex. Okay. If for every subset of unit vectors, like every subset of unit vectors defining some rank 1 matrices, let's say U1, U2 up to U capital N, there is a subset S which is delta of measure at least delta inside this subset that I'm looking at, and the expectation with respect to uniform distribution on this set S of UI UI transpose is close to rank 1. Okay? So previously, just to remind you, so assuming that the set of rank 1 matrices is convex is like assuming that the set of rank 1 matrices is 1 convex. Like if I take any subset, the expectation of UI UI transpose on that subset would be rank 1. Now I'm trying to ask for a relaxed version of it. All I want is that for every possible subset of rank 1 matrices, there should be a delta subset of it such that the expectation of UI UI transpose restricted to it should be close to rank 1. If this happens for some delta, I would say that rank 1 matrices are delta convex. Is the definition clear? Good, great. So just to remind you what close to rank 1 means, it just means that if I look at this matrix, take the top eigenvector, then this the eigenvalue associated with this eigenvector dominates in Frobenius norm. Okay? Good. So now I want to convince you that I can do this wishful thinking argument with delta convexity. Okay? And it's really trivial. Say mu is uniform again over this some subset of unit vectors, such that they were solutions to the program I care about, and say mu happened to be suppose the set of rank 1 matrices was delta convex. Then what I will do is say I could also find this set which witnesses delta convexity efficiently, while I'm wishing I might wish for everything. Then what I would do is just compute the expectation of UI UI transpose restricted to this set, take the top eigenvector and round. Okay? And just by almost construction, we have ensured that this will succeed. Okay? Now one thing we need to worry about is, in the previous argument, when we had 1 convexity, the final expectation, the entries of this matrix that we actually constructed were degree 2 moments of the distribution. Now we have to worry about whether this thing that I get out of this rounding procedure can be written in terms of low degree moments of this distribution mu. So in general it won't be, but if S is constructed out of some nice procedure, I'm going to get to it eventually, then roughly intuitively I need you to keep this number in mind. The moments you would sort of end up requiring of the distribution mu would grow as log of 1 over delta, where delta is this approximate convexity. Yes?
So is it true that any set of vectors is 1 over n convex? Like any set of n vectors is 1 over n convex?
So the approximate convexity is a notion of sorry, what?
1 over
Capital N.
was the...
Yes, because you can just take one rank 1 matrix. Yes.
So 2 to the minus d convex for dd.
Right. So I'm coming to that. I'm going to give you this trivial bounds. This is the bound that you just mentioned, that any set of vectors just trivially, because there are not more than 2 to the power of n vectors after taking some fine enough epsilon net, just taking one of these vectors would give me 1 rank 1 matrix. So it will give me that delta is at least 2 to the minus some O of n, right? On the other hand, delta is clearly at most 1 because rank 1 matrices are not convex. Okay, these are trivial bounds. You're all with me here, right? Okay, so now I can reveal the structure theorem that we prove, which is like sort of the key behind this algorithm, which is that the set of rank 1 matrices is 2 to the minus big O of root n convex. Okay, in other words, for every subset of unit vectors, there is a subset of some 2 to the minus root n measure inside this set, such that the expectation of rank 1 matrices on these vectors restricted to this set is going to be close to rank 1. Okay? Say it again?
Are you taking a uniform measure? Are you taking a uniform average? Like you take this subset of 2 to the minus root n guys, then you take uniform average of it?
Yes.
But the measure itself need not be uniform.
The measure need not be uniform, but you can always think of it as uniform by, let's say, having multi-sets of vectors. Okay, good, great. So now this is not a corollary that I expect you to see all the way through, but roughly, from where we have been talking about, you can roughly see that this will give you some, rounding that will use degree root n moments of mu. So, roughly you can see some 2 to the root n time algorithm appearing. Yes?
Just maybe for some intuition, so if we're just talking about vectors, you would sort of want them to be pointing in the same direction.
Yeah.
And so I guess for this manifold, like, do you get to play with more cancellation or something that?
Right. So in some sense, maybe one representative example is like a cap. So imagine like a cap centered at like a fixed vector, and now you have like a random vectors in some cap around it. Now in some sense, if you average out these vectors, the contributions in any direction which are like far away from this sort of center of the cap would sort of be attenuated because they happen with some tiny probability, while the center vector keeps sort of a large weight. So now averaging out will sort of make you closer and closer to this rank 1 matrix on this single vector, and this is the kind of effect you're shooting for here. Okay, good, great. So I want to tell you an example and then perhaps end. Okay, it seems like clearly it was a longer talk that I planned. So just to tell you why this root n comes from, and just to have one concrete example in mind, let's think of mu which is uniform over the plus minus 1 hypercube scaled down to be just unit norm vectors. Okay. So first, clearly, if I take the expectation with respect to mu of XX transpose, this is going to be like 1 over n times identity, which is as far away from being rank 1 as one can get. So in particular, for this set is an example that I cannot be 1 convex. Like rank 1 matrices cannot be 1 convex. But now I somehow want to go to produce some large enough subset of this set, the hypercube, such that restricted to it, the average of rank 1 matrices is close to being rank 1, right? So here is my construction. My construction is basically just take the distribution mu prime, which is mu condition on first 10 root n coordinates fixed to be, let's say, positive. Okay. So the hypercube has n dimensions. I fixed like 10 root n coordinates. So you all agree that this is a subset of size some 2 to the minus 10 root n fraction of the points from the hypercube, right? So this is the kind of delta we are shooting for. Now I want to convince you that the expectation of uniform distribution over this condition distribution, expectation with respect to mu prime of XX transpose is close to rank 1. This is what I want to convince you now. Okay, and it's like a trivial calculation because the first 10 root n coordinates are fixed. The first 10 root n by 10 root n block will be the constant entry 1 over n, right? Because of independence, I will have the cross terms being 0, and the remaining n minus 10 root n coordinates would be basically like identity. Okay. So now this part was rank 1, I can pull it out. This is the vector that corresponds to the rank 1 part. And now I somehow want to say that this rank 1 term really dominates this matrix in Frobenius norm. Okay? And this is like a trivial calculation, just that this 1 over n identity has Frobenius norm roughly 1 over square root of n, while this vector was chosen to have norm some 10 over square root of n or whatever, just because I chose 10 root n coordinates to fix. Okay? So is this example clear why I can somehow condition on 10 root n coordinates and get some subset which is approximately convex here? Great. Yes. So can I have 5 minutes? 3 minutes. 3 minutes. 3 minutes is good. I am an Indian. I learned bargaining when I was a kid. Okay, so let me try to tell you how to prove this structure theorem. Okay, and I want to spend 3 minutes because I want to introduce the third player in the title, the Log-Rank Conjecture. It had to appear somewhere. So I'll tell you how this recent breakthrough on the Log-Rank Conjecture relates to proving this theorem. Okay, so just to remind you what the Log-Rank Conjecture is, it's some conjecture in communication complexity. Which I'm not going to state. I'm going to set an equivalent formulation due to Nissan-Wigderson, which is also, by the way, the main line of attack on this conjecture. So if you care about it in some sense, this is probably the right way to start. This conjecture says the following. Suppose you have a matrix whose entries are plus minus 1 valued, okay? And its rank is small n, okay? And you should really be thinking of matrices which have like huge dimensions. So exponential in small n versus exponential in small n matrices with really low rank, so small n rank, okay? Then the Log-Rank Conjecture says that there is a submatrix of this huge matrix which has 2 to the minus polylog n fraction of rows and columns, such that this submatrix is basically monochromatic, in particular rank 1. Okay, is the conjecture clear? Great. We don't know how to prove this. There are tons of works on this. I'm not going to survey them here. But basically, 3 years ago, there was a breakthrough due to Shahar Lovett, who proved, like in some sense, the first non-trivial upper bound on the Log-Rank Conjecture. He showed that every Boolean matrix has a monochromatic submatrix with measure 2 to the minus square root of n. So we wanted 2 to the minus polylog n, we can't prove that, but we can prove 2 to the minus square root of n. Okay? And I want you to keep this picture in mind because that's what we're going to use in the next slide. A rank small n matrix can be thought of as basically having rows and columns indexed by n dimensional vectors, and the entry is given by the inner products of the vectors indexing rows and columns. Okay? And Lovett's theorem says that there is some rank 1 submatrix which is some 2 to the minus root n fraction of the big matrix. Great. So for showing you this sketch of the proof of the structure theorem that I showed you before, I'm going to assume like a wishful version of this root rank theorem where the Booleanity condition is not required. Okay? While you are with me, let's assume that the Booleanity condition is not crucial, and let's assume that this wishful version of our theorem was true. Okay? Great. So here is what I want to prove, that the rank 1 manifold is 2 to the minus O of root n convex. So again, like let's say mu is uniform over some u1, u2, u capital N. What I'm going to do is the following. I'll take the gram matrix of these vectors. Okay, u1, u2, u capital N is going to be some capital N by capital N matrix. I'll apply the root rank theorem. The root rank theorem gives me some submatrix which is defined by subset of rows and columns, which is equivalent to choosing some subset of these vectors. Right? So far you're with me? It gives me a subset of these vectors which is of sign 2 to the minus O of root n times capital N, such that when I restrict the gram matrix to just this subset of vectors, then it is approximately rank 1. Okay? And now all I'm using is that the gram matrix and the associated covariance matrix have the same spectrum. So in particular, this also yields that expectation restricted to S of ui transpose is close to rank 1. Okay? Great. So that's basically the proof. Going ahead, I showed you sort of a caricaturish version of the structure theorem. At some point I mentioned that we need to care about how does this matrix expectation with respect to the subset S of ui transpose look. In particular, we would want it to be function of low degree moments. For this we require that this construction of this set S be nice. That nice corresponds to some polynomial reweighting business that I'm not going to get into. And then this question of proving the wishful root rank theorem. So it turns out that we use a sort of a generalization of the argument due to Thomas for the proof of the Lovett's theorem or the root rank theorem, and that's probably all I'm going to say about how we prove this. But that hopefully that gives you some idea of how this stuff works. We of course have to make this work for something that we can compute. The moments of a distribution supported on solution is something not what we can compute. So this part, we have to do this part where we go back and check what constraints we used, and we can relax it to some set which can be efficiently computed, etc., etc. Not going to get into that. I'm just going to leave this slide on and finish. Thank you.
So in that delta convexity question, is 2 to the minus root n, is there a lower bound?
Awesome, that's a great question. Yes, in fact the hypercube example I showed you is can be shown to be tight. So yes, so for making further progress on this best separable state problem, in fact related problems like 2 to 4 norm or small set expansion, you need to go to some variants where you are not hit with this lower bound, and there are variants, and I can talk about it offline. But yes, as stated, the proof technique, etc., is tight. Yes.
You go. So I'm confused. Like the formulation that you had at the beginning, right? Like just a rank 1 matrix on the subspace. It's essentially equivalent to solving arbitrary quadratic equations, right?
Right.
So what is this telling you? I mean, in that setting?
Yeah, it's a great question, and I think the issue is what is your notion of approximation?
Yeah.
Huh? I think the issue is what is your notion of approximation? In some sense, we are solving quadratic equations in this notion of being close to the subspace defined by the equations, right? Like, in some sense, the norm is what makes this possible. If you have a bunch of equations, right. So I think in some sense we are looking at, I think there is a way to think of like some primal and dual, and I think when you think of this quadratic equation problem, you usually think in primal, like you want to satisfy each of the equations up to some tiny accuracy. I think the projection or the Frobenius norm thing corresponds to some dual distance, and somehow it happens to be the right thing for these problems, like 2 to 4 norm and best separable state, things like that. But yeah, in general, if you think about quadratic equations, which up to change of norm is the same question, then of course you can't expect this algorithm. We would basically have exponential hardness, I think, assuming ETH. Yes.
Yeah. So I get mean, in Thomas's proof, I guess in Shahar's proof, you have like 2 steps. You have like a discrepancy step and like a combinatorial step. So I guess you only need the first part.
So actually in Thomas's proof, there is no discrepancy step. In fact, the discrepancy thing falls out as a corollary. Okay, you can correct me if I'm wrong.
I'm not exactly sure what you mean. It's like you end
Like
up with
a
a
low
matrix
like
that's almost monochromatic.
Yeah, that.
But you need like that one theorem that if it's like almost monochromatic, then there's something big, actually monochromatic.
Yeah, that's the combinatorial.
Ah, I see. Okay, sorry. So in this application, we don't care about the difference between monochromatic and almost monochromatic. You're right. In the Booleanity case, it sort of is. First of all, it's not even a meaningful question in when the matrices are not Boolean. And in some sense, like we are all working in this approximation land, so we are okay with approximately rank 1 matrices. So yes, so in some sense, the combinatorial cleanup step of like from almost monochromatic going to monochromatic, that sort of doesn't appear in this argument. Okay.
Let's thank Pravesh again.